Hi, everybody. Welcome to this month's August edition of the Madison Astronomical Society. It's so great to see you all here tonight. My name is Lawrence Moore. I'm the president of the Astronomical Society. And before we get going, there'll just be a few routine announcements. For one of these announcements, I might want to grab Jack from the next room. So I will save his announcement for a little bit later. Um, Tomorrow we have an opportunity for those of us who'd like to go out and share the astronomy hobby with people who've never had a chance to observe through a telescope or binoculars before. Out by Mount Horeb, we are having a public outreach star party at Donald Park. And we're always seeking volunteers who might want to bring out their telescopes and share with the people there. And also be hopefully a great night. There'll be a little bit of a moon, but it'll also be a good night. Hopefully see some meteors and stuff. So that'll be going on. The event itself starts at 8 o'clock in the evening. But for those of us who are bringing telescopes, they're unlocking the gates for us to set up at about 6:30. And I will make every effort to do a weather call by 3 p.m. Does anybody have any questions about Donald Park tomorrow? Great. We hope to see some of you there with us. Um, Coming up next week, right here at Space Place, Space Place is sponsoring their own presentation on Tuesday, August 13th, 7 o'clock. Cosmic Cradles, Understanding the Formulation of Stars and Planets by Coco Zhang of the UW Astronomy Department. To begin searching for other life in the universe, we look for planets. The discovery of 1,000 exoplanets has led to a new understanding of how families of stars and planets form. This talk will present our best current understanding of these processes. So that's coming up right here in this same room at Space Place this Tuesday at 7 o'clock. Um, we have some future club events coming up on Saturday, August 31st. We're going to have our next monthly star party. We always try to do those at our dark sky site on the Saturday closest to the new moon. So this next one happens to fall on Saturday, August 31st. So all members of the society are encouraged to join us out there and do some stargazing together. And then we have a special thing. Normally, we have our meetings here on the second Friday of every month, but next month we are meeting here on the first Friday, on Friday, September 6th. And what we're going to do is a little bit different. We're going to kind of have kind of an open members discussion roundtable to talk about various functions in the society. And if John, do you want to say something a little bit about that meeting? Or?
So it's been a while since we've done like an open, like a roundtable discussion, but it's basically a meeting like this without without a speaker. So we'll have a couple of topics ready to go, but we'll also be interested in hearing if anybody in the group has any topics that they want to discuss. And it'll be moderated so that there'll be some structure to it, but it's really just kind of an open discussion because it's one week before our Moon over Monona Star Party. We'll talk a little bit about putting on a big public event too. So some of you might have questions about how does Moon over Monona work, and we'll have some people ready to talk about that. So,
Thank you very much, John. Because that's right. The following Friday on our, excuse me, while I clip my microphone back on. On our normal meeting date on Friday, September 13th, lucky us, um, we are having Moon over Monona Terrace, which is where we get basically the whole roof of Monona Terrace full of people with telescopes and electronically assisted observing setups. And we get the whole Dane County community in there. In the past, we've had 500, even 1,000, or even over 1,000 guests, depending on the weather and the turnout. And since we're doing it in early September, it'll be very comfortable weather. So hopefully we get a really big turnout. So what we're looking for, we were looking for at least 15 or more people with telescopes or electronically assisted observing uh, setups to share with the public. We're looking for at least one more person to hand out information about the Astronomical Society. And then we also are going to need a few roving rushers to help queue up lines, and because what we're going to do is we're going to try to have every telescope on the same object or a short list of objects all night long. So that way the ushers can help people um, find things that they want to see. So let me know if you're interested in helping us out with any of those rules. Contact me by email and I'll get you on the list because, yeah, well, the way the telescopes work is we reserve every spot on the roof so that we can kind of do a little bit of crowd control because things can get kind of crazy if we're not careful. So, sixth graders, man. Yeah, they'll run you over. So, it's always been a lot of fun. They're smart too. Yeah, they are. So contact me at my hiremore@charter.net email address if you want to help out. Also, um, we are kind of getting a little bit more involved with what is it, the North Central Region of Astronomical League um, conference, and every year they put on somewhere kind of a regional meeting, and they're always looking for speakers. So contact us if you think we've always had a lot of members put on good presentations here, and the people at the NCRAL would be more than happy to hear your presentation at one of their events. So let us know if you'd like to participate. Speaking of such an organization, Jack, do you want to say something about our recent decision to become a affiliated member of, what?
As you may recall, at last meeting, I requested the board spoke about the Astronomical League. And on Wednesday, the board held a meeting and we have decided to rejoin the Astronomical League. It's going to be a little bumpy at first because their membership year is a little different than ours. But on the during September, where's Jurgen? Jurgen will send out a form to re-up your membership in MAS. And this year that will include an option to pay small additional fee. You'll become a member of the Astronomical League. So I'm delighted with the decision. It was a unanimous decision by the board. Some work on our part to get there. Um, I think it's going to be a very good benefit for all of us. Thanks.
I agree. And over the last few years, more and more members of our society have been active in the Astronomical League, and it's the regular yearly extra fee. The club pays only a small fee to become an affiliate club, and then it's and there's an option to pay an extra $9 per year normally, although the exact number for this year is a little bit, because I guess we just got heard from the league that they said that they're willing, or what? Oh, yes, Jurgen? Um, there's a problem. Jack sent out an email about that. I don't want to make fun. Okay, so when you sign up for the astronomical league, you sign up. We're going to take 2 years. Okay, so that's what. Because you'll end up getting. All right. So we've been actively what Jurgen was just talking about. We were just actively communicating with the Astronomical League, and they gave us some options. But for us, the best option is to be for just this first year when we sign up, since their membership year starts in July, but ours starts in October. For the first year, when you sign up, it's going to be a a 2-year membership. So you'll see that when you get your renewal forms this year, and also on the new sign up forms for club membership on the website, you'll see that. So that's the way it's going to work. So does anybody have any questions about the Astronomical League? All right, very good. I'm trying to think if there's anything else to cover. Is there anyone here who has never visited the Madison Astronomical Society before and would like to introduce themselves? I will be right with you. Yes, we do have the sign up sheet being passed around. If you're a member or a guest, please feel free to sign. Yes, who are you and what do you do?
Uh, Hello everybody. So my name is Ken, and I'm an incoming graduate student in Madison, and I'm gonna be working on astronomy.
Great. Pleasure to meet you. And for if anyone here is a UW student, they do have a UW Astronomy Club. So look them up and it'll be lots of fun opportunities.
Hi, I'm Zach. I'm also a UW physics PhD student. I work on that telescope with Justin, actually.
How cool is that? There's a good chance that John might come and talk to you and at some point and try to get you do a presentation on that. So, Kyle, it's nice meeting both of you. Welcome to Madison.
Hi, I'm Ainsley. I'm Justin's sister. And usually I'm not in town, but I get to be in town from New York, so I'm so excited.
Thanks for visiting us. It's great to see you. Anyone else? Is there anyone else who'd like to introduce themselves to this astronomical society? I guess not. Hearing none. And we got a couple minutes to kill. Does anybody have any special announcements that they would like to share with the members of the club? Or oh yes, Chris.
Hi, I'm Chris Zeltner, and I'm going to be running our picnic the end of September. And I'm looking for a little help the day of the picnic with like grilling and setting up. So if anybody can give me a hand, I would appreciate it. Um, thank you. We have a nice picnic. The club provides some meat, hot dogs, brats, and burgers. I usually bring barbecued chicken as my donation, and then the rest of it's potluck. And we provide the plates and silverware, and you provide your own. Oh, we provide some beverage, but mostly you provide your own. And a star party.
Yes, yeah, and as I was saying earlier about the monthly star party coming up towards the end of August, and I can't remember the date. The one for September that we're talking about for this picnic will be on, I believe, September 28th. It should be the last Saturday of September. And I think we're also going to tentatively do the Sunday after that as a rain date in case the weather's bad on Saturday. All right, let me know if you have any questions about that. If not, I see it's just about 7:30, and I guess we're ready to introduce tonight's guest speaker. It's my fault.
So, Justin, I probably asked you 1,000 questions in preparation for tonight. I didn't ask you how to pronounce your last name. Vandenbroucke? Okay. So, as you can see, our guest speaker tonight is Justin Vandenbroucke, Department of Physics at UW-Madison, Associate Professor. And he's got the high energy thing up there, but working with gamma rays and neutrinos primarily. And I'm very excited to hear Justin's talk, so I'm not going to go on any longer. Please welcome Justin Vandenbroucke.
Can you hear okay in the back now? Great. Thank you very much to the Society for the invitation. I'm excited to tell you a bit about the research that I work on. I'm going to focus mostly on the very big picture, motivation of the science that we do, including some of the technical work that we do on this particular telescope that Zach mentioned earlier. It's kind of a strange looking telescope. It detects not light directly, but indirectly detects the highest energy some of the highest energy photons in the universe, gamma rays. And it does that by detecting some light that I'll tell you about that's a secondary product of gamma rays. Bounces off of the first mirror here, off of the second mirror, and then onto a camera here. We work on especially here in Madison, just a couple miles from here in Chamberlain Hall. We inaugurated it in 2019. You can see the big party we had for that. There were 4 or 5 people in the audience in the anticipation of this party here in this photo from Madison. I'm going to start with some preliminaries. I know that you all are very familiar with astronomy and a lot of the basics, but as you learned, I also invited some of my family members here. And so I want to make sure that we're all on the same page and bring them up to speed. So let's start with some basic facts. So especially this time of year, we're familiar with this basic fact. So light travels much, much faster than sound, but not quite instantaneously. And we can see and observe with our own senses that fact. So let's put some numbers to that. So the speed of sound in the atmosphere is about 800 miles per hour. Speed of light is about 700 million miles per hour. That's equivalent to infinite when we're watching fireworks or for most of our daily experience. But you can experience the difference between the speed of sound and the speed of light. So suppose a firework explodes a typical distance that you're watching it, which is about 1,000 feet away. So it's static on the line. Be my pocket. Take it out of my pocket, is that better? Okay, how's that? Okay, suppose the firework explodes about 1,000 feet away, a typical number. That means that the light arrives a millionth of a second after the explosion. You're not going to experience the fact that it took more than 0 time to travel from the firework to you. But the sound arrives a full second later. So that's why you experience this as flash and then the boom a full second later. You can tell that difference. And not only that, but you can use that. So, okay. Speaking of explosions and pops. Yeah. Leave this not in my pocket. Okay. So you can even use this information to calculate how far away it exploded. Since you know 1,000 feet distance, sound rather travels at 1,000 feet in 1 second. That means that 1,000 feet, you can think of that as equal to 1 sound second. So you can use this difference to map time onto space and use this unit that we usually think of as a unit of time as a unit of distance. So the sound second is a unit of distance. Not only that, but imagine that you experience fireworks without the light or without the sound. So this is a multi-sensory experience. We want to experience both, ideally, if we can, get the full experience of the fireworks. So that's a theme that we'll come back to. Light and sound provide different information. They're different messengers. So I know we're only a minute in, but I was warned this is a certified nerd audience. We already have a quiz. How far away is the sun? Uh-oh. You choose the units. That's a good one. I heard 8 light units. That's 8 light minutes. That's true. 1 AU. That's lazy but true. 93 million miles. Yeah. And you already got this one. How long does it take to light to reach us from the sun? 8 minutes. Okay, so pretty far away, much farther than the firework. So we can really tell not only with the speed of sound, but even with the speed of light. Light travels at a finite speed. So the sun is 8 minutes away from us. 8 light minutes away from us. We can come closer to home. How far away is the moon? Maybe a little bit harder quiz. Great. 200,000 miles, 1 second. So light travels about a second from the moon to us. Okay, going the opposite direction, how about farther distances than the sun? What's the nearest star other than the sun? How far away is it? Wow. Pretty good. How about in miles? Yeah.
Should be using a metric system.
Okay, that's fair. 40 trillion miles or 4 years. Okay, so we can see that this sets the foundation for light travel time and distances in astronomy. So light takes a second to reach us from the moon. That means the moon's 1 light second distant. Light takes 8 minutes to reach us from the sun. The sun's at 8 light minutes distant. We can also zoom out farther across the galaxy. It takes about 30,000 years for light to reach us from the center of our own galaxy. So the galactic center is 30,000 light years distant. There's another interesting galaxy. So now we can go to galactic, intergalactic, extragalactic distance scales. Light takes 50 million years to reach us from a particular distant galaxy called NGC 1068 that I'll come back to. So that galaxy is 50 million light years distant from us. Okay, some more preliminaries. Electromagnetic spectrum, the photons across the electromagnetic spectrum, also known as electromagnetic waves. First, we have the rainbow all the way from red through blue to violet. But we can zoom out beyond that as well. So beyond visible light, if you go to the long wavelength end, you get beyond red, you get to literally beyond red, infrared. Keep going, get to microwave and radio. Go in the opposite direction, beyond violet, you go to ultraviolet, and then X-ray and gamma ray. And so wavelengths increase from right to left, frequency and energy of the photons increase from left to right. And this is the picture that we often have, but it's kind of unfair to gamma rays. You just have this little tiny slice over here. Really, if you put this on a linear scale, even if you be a little bit more charitable and put it on a log scale, gamma rays take up a lot of space here. So I was at a talk once and someone said, what's beyond gamma rays? And I said, unfortunately, we don't have another name for what's beyond gamma rays. It's just gamma rays all the way out. And there's a huge amount of space here that gamma rays take up. So it's kind of unfair that we only get one name. We actually cheat a little bit. We divide it into high energy gamma rays, very high energy gamma rays, ultra high energy gamma rays, and so on. Because I guess, yeah. So to visualize that a little bit, we have in units of electron volts, that's basically particle physics units. An electron volt is basically the energy of a visible optical photon. You can see with your eye. And we measure in thousands, millions, billions, trillions, even quadrillions of electron volts. So we're seeing the universe literally quadrillion times beyond visible. And I think it's unfair that we only get one name for all of this. So 10 orders of magnitude in energy that we spend. You can put the rest of the entire electromagnetic spectrum that all other astronomers use side by side. We don't span quite as large as it does, but almost. So basically, we span almost as many orders of magnitude as all of the rest of the electromagnetic spectrum that astronomers use. So we want to use all of the electromagnetic spectrum to start with. We want to see things across the entire spectrum and get all the different information, learn about things the best we can from that. Starting with people. So here's a scene of a person. You can see the person in visible light. But it's actually a sort of a complicated thing going on here when you think about the physics of it. You might think you just turn on the light in the room, you see the person, it's straightforward. But really there's photons that are produced by ambient light or by a light bulb. They're bouncing off of the person, and they're telling us information about how they bounce off. The way that they bounce off tells us about different aspects of the person, how they look. And so there's actually a lot of interesting stuff going on here. There's reflection of the photons off of the person. We call that scattering in physics. And you need a light source for that all to make sense. Here's the same person if you turn off the lights. And so this is all the physics of scattering. So really, we need to understand the physics of scattering to interpret these images. The same person viewed in infrared light gives you a totally different image of them. So you can see something about how warm they are, that they're warm-blooded, they're not cold-blooded, at least literally speaking. I don't know much about this particular person. So the same person in infrared light, you get completely different information. You get information about their temperature and about the thermodynamics of the situation rather than just a optical image. And this is emission. This is not light scattering off of this person or bouncing or reflecting. It's being literally emitted by the person. So that's the physics of emission. That's going from visible to infrared. We can also go in the other direction from visible to X-ray. So here's a picture of a person, the visible photons again scattering off of the hand. We know something about the physics of scattering, so we can infer information about the hand. If we take an image of the same hand in X-rays, then we're using the physics of absorption. So X-rays can travel or not travel through the hand material depending on what it's made of. Not only its density, but also its chemical composition. Bones have a lot of calcium, so that tells us where the bones are. So we're learning a lot about people by viewing them in different wavelengths. And this is all due to the different physics of emission, scattering, and absorption. And I think we've all had the experience that if you look at someone, you get a lot of information from them. You look in these different wavelengths, you get even more information. But if you only look at them, you probably get an incomplete or even inaccurate impression of them. So you should also listen to them. You should use multiple senses, get a better idea of what they're like if you listen to them in addition to look at them. And you might want to use even more senses. You might want to use touch, smell, taste, depending on how well you know the particular person. So the basic idea is we need to use all of our senses to get as much information about the world around us as we can. The entire electromagnetic spectrum and all the other senses in addition to sight. Okay, so most light in astronomy is like that infrared image. It's not scattering necessarily, but it's emission, and it's emission specifically due to temperature. So we saw the infrared image where different parts of the body are glowing different amounts due to different temperature, and then whether there's clothing in front of it or not, and so on. And this is like a lot of our intuition from everyday experience with different temperatures of hot objects, whether they're very hot or kind of hot. They literally glow red hot or even yellow hot or blue hot. And so a red star is like 3,000 Kelvin, a yellow star is like 6,000 Kelvin, a blue star might be 18,000 Kelvin, and so on. What about a red fish or a blue fish? Are those colored because of corresponding temperatures? Yeah, so this is going back to the physics of reflection rather than the physics of emission. So sometimes you need to be a little bit careful that not everything is just temperatures. There's the physics of emission in the top row. It's of scattering or reflection in the bottom row. But most astronomy that we do is using this idea of thermal radiation and colors corresponding to temperatures. And you can make that quantitative. So here in the vertical axis is how hot something is, its temperature, and the horizontal axis is the increasing frequency or energy of the light that it emits. And we can go all the way up through the entire electromagnetic spectrum, from radio through millimeter, infrared, visible, ultraviolet, X-ray, gamma ray, and so on. The gamma rays that I'm talking about tonight are literally off the chart. They're way up here, very high energy gamma rays. So what do you think is producing them? Supernovae? Could be supernovae. What's the physics of the emission? I think it's also temperature and thermal radiation.
Like something compared to something more static, like a pulsar or something like the gravity on the pulsar and gravity below.
Yeah.
Very strong gamma ray emitter, but it's been kind of doing its thing for a very long time.
Yeah, so we'll talk about pulsars, including do you think, is it emitting gamma rays because it's very hot, like off the charts hot? Yep. Yeah, among other things. So the basic idea is it's not thermal radiation. We call it non-thermal astronomy. So you don't need to remember the details of all this. Synchrotrons, number one. Basically, it's particle physics processes. So this whole field is of high energy astrophysics, multi-messenger astrophysics. It's combining particle physics with astronomy. So it could be electrons interacting with magnetic fields to produce the gamma rays. It could be low energy photons interacting with high energy electrons to produce gamma rays. It could be energy electrons interacting with protons to produce gamma rays. Could be a high energy particle, a subatomic particle called a pion, decaying to produce gamma rays, and so on. So basically, there can be particle physics interactions that are happening. So produce these things, you need very high magnetic fields, very energetic electrons, or very energetic ions, and the particles that produce them. So that tells you, if you detect these very high energy gamma rays, it tells you that one or more of these processes is happening, which is very different from just it's hot, therefore it glows, which is most of what we see on the night sky. There's a fifth mechanism that we haven't yet detected, at least I don't think we have. Some people saying that we have. There's tantalizing hints of it, and that is dark matter. So dark matter might be a particle that decays or annihilates to produce gamma rays, among other particles. So we're also looking intensively for that signal. We could finally understand the nature of what most of the universe is made of through these gamma rays. So fleshing out this idea that we want to look at people to understand them best, we want to talk to them, not only look at them, maybe also use the other senses. We want to do the same thing to the universe, but we'll start with the entire electromagnetic spectrum. So look across all the different bands of the electromagnetic spectrum. So here are some basic maps of what the universe looks like in the different bands. If you make an all-sky map of the universe in visible light, you can see lots of stars, maybe some galaxies. You can see that there are these dark lanes so the plane across here is, of course, our own galaxy, the Milky Way. That's the projection that it's rotated to here. And you can see these dark lanes where dust is obscuring the view of the otherwise bright stars. So you can see a lot about our own galaxy and beyond. If you switch to infrared light, you get a complementary view. You can see the Magellanic Clouds. You can also see the Milky Way. You can see this bright region in the center. And we start to see different aspects of dust that is either glowing or absorbing, depending on the wavelength you're talking about in the infrared. If you keep going long wavelengths, you go to radio waves, including microwaves, you start to see back in time to basically the remnants of the Big Bang, just a few 100,000 years after the Big Bang. And this was a beautiful Nobel Prize winning discovery that the universe glows in this cosmic microwave background as radiation as predicted by theories about the hot plasma that was formed early in the universe. If we go to long distance radio waves, this is actually now going in the opposite extreme from gamma rays. So these are such long wavelengths that it's hard to explain with thermal radiation. And indeed, this is non-thermal radiation, also by synchrotron radiation. So charged particles, electrons that are interacting with magnetic fields to produce this radio wave emission. You can see these beautiful long wispy rings coming out of the galactic plane. If you go in the other direction, away from visible to the ultraviolet, go to shorter wavelengths instead of longer wavelengths. We see this view, you can see the Milky Way. Then here you can also see the plane of the ecliptic. And you can see lots of different stars, basically stars that are glowing. Now they're very hot stars that are glowing in the ultraviolet in addition to the visible. And we can also see the Magellanic Clouds here. Keep going to X-rays. We're getting into pretty energetic processes that can produce the X-rays. There can be a combination of some thermal emission, but also non-thermal. Synchrotron emission, for example. Also, Bremsstrahlung was one of the names in the other ones. That's basically interactions of the electrons with protons instead of with magnetic fields. And we keep going and we get to one of my favorite images, the gamma ray universe. So you see some of the familiar structures of before. You see the Milky Way plane. You see individual dots within the Milky Way. Those are individual sources within our galaxy. You also see diffuse emission. That's from cosmic rays colliding with the interstellar medium to produce pions that decay to produce gamma rays. That was one of the mechanisms I mentioned before. You also see this population of very bright little dots of light that are kind of isotropically distributed. Any guesses what those are? Galactic nuclei. Yeah, so active galactic nuclei. These are giant black holes at the center of distant galaxies that surprisingly, black holes power the brightest objects in the universe. Feel free to jump in with questions, by the way. Okay, so how do we do these different types of astronomy across these different bands, especially in the gamma ray? Oh, just to remind you, gamma rays start at about 100 keV. That's roughly the line between X-rays and gamma rays, and then go all the way up to quadrillion. That's 10 to the 15 electron volts. So literally all the way up to a billion, a trillion, even a quadrillion. Just in the last few years, astronomers have detected light a quadrillion times higher energy per photon than we can see with our eyes. So you can imagine how much that opens up in terms of this little factor of 2 that we can see in wavelength with our eye compared to quadrillions of times beyond that, something that we could never imagine seeing with our own eyes. So as you know, there are both ground-based telescopes and space-based telescopes. Of course, that's because of what you can see through the atmosphere or not through the atmosphere. So the vertical axis here tells you the capacity of the atmosphere. So a lot of brown means the atmosphere completely blocks the light. A lot of blue means that the light can get all the way through it. So there's one prominent band here, of course, in the visible. That's where the sunlight makes all the way down to Earth, and that's why we evolved to be able to take advantage of this band and detect that light there with our eyes. Also, some radio waves are observable by Earth. Some little windows of other bands here. You can see much of the spectrum is not observable by Earth because it's absorbed by the atmosphere. And that includes the infrared spectrum and ultraviolet X-rays and gamma rays, the highest energy, shortest wavelength part of the spectrum. So to detect these photons directly, we have to go to space. You might already be wondering why the first image was a telescope on the ground. I'll come back to that. So the basic physics of how we detect these gamma rays, we have Einstein to thank. So basically a gamma ray collides with matter and it converts into an electron and a positron. So the light is disappearing. And think of that light as a pure form of energy. It's like kinetic energy without any mass. And it produces two particles that have mass, an electron and a positron. So that's directly using E equals mc squared. With enough E, as long as this gamma ray has enough energy, you can make the mass of the electron and the positron. And that's a relatively low energy in the perspective that I'm speaking from today. You only need about 1,000,000 times the energy of a visible photon. So these ones that are billions, trillions, quadrillions of times higher have plenty of energy to do this process. So that's one preliminary. We need to understand how these detectors work. Another one is called Cherenkov radiation. This is, I'm sure most of you have been to the Memorial Union Terrace. This is a picture I took on a calm day a couple years ago in the summer. A duck enjoying the terrace, swimming by, and you can see if he were stationary, if he were standing still and paddling his legs furiously, there would be ripples emanating outward in a circular pattern. It's a little bit more complicated because he's swimming forward. He's still kicking his legs, but he's swimming forward. And so those circles are still radiating outward. It's just that they're radiating outward from a different point, every point that he's at on his path. And so those waves add up into this triangle that they form behind him, the same as the wake of a boat. It's the exact same physics that explains sonic booms from a jet and also Cherenkov radiation. So it's waves on the surface of water in this case, waves of sound in the sonic boom case, electromagnetic waves in some material like water in this case. So here you might have seen movies about nuclear reactors that have a blue glow. That's the blue glow of Cherenkov radiation. It's due to energetic charged particles that are traveling faster than light travels in that material. Light travels a little bit slower in water than it does in vacuum, but the particles are traveling faster than that, very close to the speed of light. So that's why they produce blue glow. And this is the workhorse for many different projects in particle astrophysics or very high energy astronomy. I think you've had talks about IceCube, also this one today about gamma astronomy. We use Cherenkov radiation for a lot of different purposes. Now, putting these together, we can explain why. I'm going to start here. So remember the gamma ray converting into an electron and a positron, that was one concept. The other is emission of Cherenkov radiation, that's a second. And let's put those together. So if you launch a simple particle detector into space, put it in orbit around the Earth, for example, if the gamma ray collides with it, it can produce an electron and positron, and then you can use particle physics techniques to detect that signal. And so that's what one very successful satellite that I've also worked on called Fermi, launched by NASA in orbit around the Earth, does. It basically just convert the photon into electron and positron and then detect them. That works for billions of times the energy of the visible photons. If you want to go to even higher energies, photons become much more rare, and you can't collect them with an instrument that you can launch into space. However, the flip side of that is that it's such a large signal that those two, that electron and positron, continue, and they initiate a chain reaction. So they convert their energy into additional subatomic particles by colliding with other materials, and the whole process continues. So in the middle image here, that's what we call an air shower. That initial electron and positron produce additional particles, they produce additional particles, and so on. Those particles now act like the charged particles in the nuclear reactor, and they produce a flash of Cherenkov radiation. Now we've got a flash of visible Cherenkov radiation that we can collect with a somewhat traditional telescope. So that's the idea of telescope on the first image and also imaged here in the center. So the Cherenkov radiation is collected by this telescope, focused onto an instrument at the focus. We call it a camera because it's at the focus of a telescope, but it doesn't look like anything you think of as a normal camera. And then we can measure those very high energy gamma rays. At even higher energies, or also overlapping with this energy range, we can build an array of detectors high on a mountaintop and directly detect the particles in that shower of particles in the atmosphere, rather than needing to only detect the Cherenkov radiation from it. These two techniques are very complementary. The one on the right can see a larger fraction of the sky at once, but with worse sensitivity. The one in the center has to point in a particular region of the sky, but it has exquisite sensitivity when it does so. So now fleshing out that middle technique a little bit. Here's a picture. The gamma ray comes in, converts to electron and positron, produces this basically chain reaction with lots and lots of particles in the atmosphere. Most of them are emitting Cherenkov radiation. The whole burst of Cherenkov radiation reaches the ground level and illuminates the pool on the ground, and these telescopes can collect it and focus it onto their cameras. And if we have multiple of these, we can collect the gamma rays more abundantly, and we can also determine the information about each one better.
Question.
Yeah.
On the instead of just the subatomic particles, wouldn't some of the positrons and electrons also recombine in that scenario too and just create energy?
Yes. Eventually that would be the case. These are such high energy that they rarely have a chance to do that. They typically, like an electron, will typically collide with another atom in the air first, with the nucleus of the atom, emitting another photon before it'll have a chance to annihilate. Similar with a positron, before it has a chance to annihilate with an atom that it finds with an electron that it finds in an atom somewhere. So they would in principle annihilate eventually, but most of them don't have a chance to. Any other questions for now? Okay, so these are really fun instruments. You saw one photo at the beginning. They're located in places around the world that are similar to where some of the best optical telescopes are. It's basically detecting Cherenkov radiation. You need a high, dry, low, good weather, low light pollution site, similar to optical astronomy. Good thing is that you don't need as good angular resolution of the mirrors. So many of these telescopes are as large or larger than Keck and some of the other largest optical telescopes in the world, but you can build them very affordably because you don't need as exquisite imaging resolution. So the one that I work on is at a site near this other telescope called Veritas in Arizona. There's also one in Namibia called HESS and one in the Canary Islands called MAGIC. Here's some pretty views from those sites. Now this whole field is really a hybrid between particle physics and astronomy. And that's true of the concepts that we need to understand and that we apply. And it's also true of the instrumentation that we build. So from far away, these look like normal telescopes. They've got a dish of segmented mirrors and they've got a camera at the focus. And when you look at the camera, you open it up, it's got a bunch of photomultiplier tubes. These photomultiplier tubes or other sensing devices can detect individual photons of Cherenkov light because it's a pretty quick and dim signal. And they can do it with the billionth of a second time resolution. Okay. Try the other one again. Yeah, it's like it's suddenly flared up. All right. So I was saying that the camera looks like a particle physics instrument. It basically is. It's using sensors and electronics, really with particle physics heritage. So single photon sensitivity, nanosecond timing resolution. And what we combine all that technology from the telescope and the camera, literally make a movie of this particle shower in the atmosphere developing across the atmosphere. And by recording that movie, we can then infer the direction and energy of the gamma ray and do astronomy using those gamma rays. Now I've shown you some of the current instruments. The next generation instrument that's now already under construction and in fact operating in its initial phase is called the Cherenkov Telescope Array Observatory. So the photo that I showed you at the beginning in Arizona is a prototype for this array. You can see that's here, the one that I showed you at the beginning, and it will be combined with other telescopes using the same concepts but optimized in different ways. So for the lowest energies, we need the largest telescopes. For the highest energies, we can get away with smaller telescopes and we can build more of them across a larger area for the more rare highest energy gamma rays, and then intermediate between the two at medium energies. And so you can see just with this array of different instruments of different sizes, but the same basic concept and same basic technology, we can span several orders of magnitude, about 4 orders of magnitude in gamma ray energy, which I think should count as multiple bands of the electromagnetic spectrum. So here at UW-Madison, we play an important role in this observatory. We're especially involved in the camera that's at the focus of this instrument. When we first were developing it, it was in the lab in Chamberlain Hall, a couple miles from here. And in the first iteration, here are some of the people in my group who are involved in that. You can see we call it a camera. Hard to visualize when you say that. People think of like a handheld camera or even a camera in an optical telescope, but really it's the size of like a mini golf cart or something like that, or a golf cart. So here's the focal plane. We have sensors that are instrumented there, and then electronics behind it. You can see here a student behind it working on that electronics. And then we took it to the telescope in Arizona and lifted it up onto the telescope there a few years ago. And there's that inauguration photo again. You can see another sense of scale here, the people in the foreground of this telescope. It's a 9.5 meter diameter primary dish. So that's very comparable to Keck in Hawaii if you've been there or seen photos of it. A world leading, very large optical telescope. I mentioned that we're making movies of these showers developing in the atmosphere, and UW put together a little promotional video when we were developing that camera in the lab before we shipped it. And I had a quote in the middle where I said, I'm sure as soon as we turn on the camera on the telescope, there will be all kinds of problems. We'll need to spend months debugging it. It'll be fun to figure out what's wrong and then get it to work. What happened instead is we had this inauguration, we had a big party. The mirrors had been covered during installation. The camera had just been installed, and then the mirrors. The mirrors had not been uncovered yet, let alone focused. So the instrument wasn't even focused yet. We installed the camera, we finished the party. The next day we turned it on and it worked right away. So I was wrong in a beautiful way. So what was that? Yeah. Same reason I like to to bet against my grad students and other collaborators, because it's win-win. So this is a video that I'm going to show you of one of these particle showers developing in the atmosphere without even focusing the mirrors yet, without focusing the optics. So it's not a high quality image, but you can see it there in the bottom left. So that whole image just lasted a few billionths of a nanosecond, a few billionths of a second, maybe 10. Oh, there it is. So the whole flash, so the full duration of the movie is 50 nanoseconds, 50 billionths of a second. And the flash itself, you can see only occupied a fraction of that. Then we thought it would be good to actually focus the mirrors to make a much better image. That was a long process that took a couple years by our colleagues who focus more on the optics in the same way we focus more on the camera. They have a really cool process. They intentionally defocus the mirrors in order to they pointed a bright star. They defocus the mirrors in order to make multiple independent images of the same star. And then they can move the mirrors back and forth and see how that moves the star image. And they can do all this fancy matrix math led by a Russian professor. And then they figure out how to tilt all the mirrors to bring all those star images directly into a single beautiful bright spot. That's what they did here. Yeah. So what science can we do now that we've built this and then actually align the optics? I'll come back to that, but we need to go back to some preliminaries. First, pause for any other questions.
What was the angular area of the sky that you were looking at in the initial challenge?
It's about 2.5 degrees across. So that's one nice thing about these two different mirrors that we have. This is only instrumenting a fraction of the field of view. We're upgrading it now to get 8 degrees across. So it's a pretty large field of view. So I need to go back to some preliminaries now at risk of insulting the certified nerds. I want to bring my family up to speed again. So we need to go through the basics of how stars live and die to get to the science that we're doing. It's really about the lives and deaths of stars. So what happens when a star dies? It starts as basically this nebula. Gas collapses to form a star. It can either form a typical star or a very massive star. Eventually, as it burns all its material, it eventually gets much larger, goes through a giant or supergiant phase, and then it can die. We often think of that happening as a supernova. It can also die even more spectacularly than a supernova as a gamma ray burst. When it does that, it leaves behind a dead star called a neutron star or even a black hole. However, it can also just blow out its outer atmosphere and produce what's called a planetary nebula. It's a misleading name, much to do with planets, but it has historical reasons for that, leaving behind a white dwarf at the center. So that's another type of dead star. Do you know what will happen to the sun at the end of its life? Planetary nebula. Yeah, it's not massive enough to go supernova, so it'll become a planetary nebula and a white dwarf. So white dwarfs are one type of basically a dead star. It's like the core of the star that's left behind after the atmosphere is blown off, and it's very bright. So here's a binary stellar system that has a bright star and a companion. That companion is the white dwarf in this case. And it's very, very dense, 1,000,000 times more dense than water. So white dwarfs are great environments for testing our basic understanding of physics under extreme situations. This is a beautiful image, but what it blows out to the outside is even more beautiful. I'm sure you've all taken photos of these and studied photos of them. Here's one planetary nebula. The Eskimo Nebula. That alert up in the top is too annoying. I guess we can just live with it. Another planetary nebula, the Cat's Eye Nebula. Another one, the Ring Nebula. I think these are some of the prettiest images in astronomy. The Hourglass Nebula. The Lemon Slice Nebula. I wonder how they named that one. Martini Nebula. And you see 6302, very different shapes and forms and colors, even better than the fireworks in the beginning of the talk. So you might think it's a little sad that our star is not even going to bother to go supernova, but I think I take some solace in the fact that when our solar system dies long in the future, it will eventually lead to amazing, beautiful images like this that someone in some distant astronomical society will discuss photos of. So here's an actual supernova. They're also pretty, maybe not quite as pretty, but also pretty beautiful. So when the star evolves, it produces lots of elements. It burns thermonuclear reactions and produces elements. And then when the supernova happens quickly, it continues that to even heavier elements. And then it explodes and disperses all those materials into the universe. And then some of those collapse into new solar systems and so on. So it's this beautiful repetitive cycle. And there were these musicians that sang, "We are stardust, we are all made of stars." And it sounds like some woo poetic lyric, but it's literally true. I think that's really amazing that we're made of stardust and stars.
So, certified nerds, that song was originally written by Joni Mitchell, you know.
I didn't, thank you. CSNY's version is is beautiful, but thank you. Is there another?
Is that serious? The
Yeah,
the
White
guy for
Dwarf.
the white dwarf. Okay.
Yeah, that's serious.
Is the light coming from planetary nebulas emission? Is it thermal?
Yes, it's basically thermal emission. Yeah,
Slowly cooling off.
yeah. Complicated by atomic transition lines that make the different colors. Okay, so coming to supernovae, probably a lot of you have heard this story, which is a little controversial now, but one idea of it is I was in Chaco Canyon about a decade ago, and this is famous among a lot of astronomers. There are these pictographs here, and there's a photo of a human hand, probably a moon, and some maybe a bright star. And from dating this, it happened at the same time. It happened in 1054 AD. So there were maybe some astronomers living in Chaco Canyon then, made this pictograph, and we know that there is a remnant of a supernova that happened around then, 1054 AD. So maybe these really were astronomers marking that event back almost 1,000 years ago. And we're going to zoom forward a minute into the modern age of that instrument I just explained to you. Before that, though, here's a contemporary photo uh, with the Hubble Space Telescope of the Crab Nebula. So this is the remnant of that explosion. A supernova that formed a neutron star at the center. You can see this remnant of the explosion still going outward with these beautiful colors. And so that's what it looks like in optical light, almost 1,000 years later. A little bit more about the physics of the supernovae. So during the supernova, the stars turn into neutron stars. So those are even more dense than the white dwarfs. Neutron stars are 100 trillion times more dense than water. So it's basically the mass of the sun, like hundreds of thousands of times the mass of the Earth, but collapsed all the way into something smaller than Madison. So imagine what it's like to that environment. Physics is beyond what we can comprehend pretty much, and it's a good test system for our understanding of basic physics. In addition to supernovae, some of the most violent explosions of the stars at the end of their lives are gamma ray bursts rather than supernovae. And they are basically a spectacular explosion that results in either a neutron star or a black hole. And this is one of the main ways that we know black holes form, through the dust of stars. When the very massive, most massive stars die, they produce black holes. And when I was in high school, I was reading about black holes, Stephen Hawking books, and so on, and they were still pretty hypothetical. They were kind of mathematical constructs. Now we don't know that there are many black holes throughout the galaxy, like these left over from stellar explosions. And even at the center of every galaxy, there's a giant black hole. It's still a mystery how these form, but at the center of every galaxy, including our own, there's what we call a supermassive black hole, millions or billions of times the mass of the sun. So there's an illustration of what it looks like on the right, photo on the left, and the basic idea, these somewhat surprisingly glow as the brightest objects in the universe, black holes do. So somehow they're powering that really bright emission. It's kind of like if you pull the plug on a cosmic bathtub and the water spirals down into it, the matter spirals down into it, but it's accelerated to such extreme speeds that it starts forming complicated interactions of particle physics and magnetic fields and plasma physics, and it forms this disk of matter falling in, but it also shoots out these bright jets of particles and matter and radiation. So somehow these are some of the brightest objects in the universe. We don't really understand how. So I want to come back to some of these topics that I've just touched on as background now with our modern instrument that I've explained. So coming back to the story of the telescope in Arizona, we turned it on despite not focusing the mirrors. We detected particle showers. We focused the mirrors. We brought that beautiful star image into focus. Now we could actually do gamma ray astronomy. Something I didn't mention is that particle shower we saw is actually from a cosmic ray. It's not from gamma ray. So the Earth is bombarded with cosmic rays, and they produce particle showers in the same way as the gamma rays. We need to distinguish the two, and we need really good imaging to do that. So that's why we needed the better imaging. And then we pointed at the Crab Nebula. And when we did that, we saw these even more beautiful little particle showers. Each one of these is now time integrated. I time integrated the movie. And you can see they're these sort of oblong, almost elliptical shaped time integrated showers, and they're all pointing back to the source. You can even tell they're pointing a little bit off of the center. We thought we were pointing at the Crab Nebula, but when we used star images to figure out exactly where we were pointing, we could perform a slight correction. And we confirmed that the Crab Nebula was actually slightly off center in the direction of all these showers. So combining all these different gamma ray images, we can actually calculate the direction where each one came from and make an image of the Crab Nebula itself. And when we do that, we get this pretty simple image. So it's nothing to compare with the Hubble Space Telescope. We see this bright dot of light in the center. And that's telling us not much about the shape of the emission. It's consistent with the angular resolution of our telescope. It's just a single bright spot. But it tells us that this thing in the universe that exploded 1,000 years ago, that maybe some Chaco Canyon astronomers observed 1,000 years later with this cutting edge instrument of astronomy and particle physics, is detecting photons that are trillions of times more energetic than we can see with our eyes. So just that basic fact is revealed by this point of light here. Other instruments, like the wide field one that I showed at the beginning, there's one that uses that technique. It's called LASSO. It detected a couple years ago, it detected emission from this Crab Nebula at even higher energies, at 10 to the 15, a quadrillion times more energetic than we can see with our eyes. So there's some really amazing physics going on here. Moving on to other science that we can do with these types of instruments. I mentioned that black holes can form at the ends of the lives of stars when the stars explode and they leave behind a black hole. Sometimes that happens, so stars form in clusters. They form from these big gas clouds initially. It's likely that stars form near one another. And it's likely that they capture each other in orbits and they become binary or even triple systems. And so lots of stars are in binary systems. And then if one goes supernova, then you have a black hole plus a star. If they both go supernova, then you have two black holes and so on. So it's common that you have two black holes and they are attracted to each other and they radiate gravitational radiation. This is all hypothetical according to physics, and therefore they should fall into each other as they lose energy to gravitational radiation. It was all hypothetical until 2015. I'm sure you all followed the news then. The first direct measurement of gravitational waves. So these black holes had lost all of their angular momentum through radiating gravitational waves, and then they fell in their final death spiral into one another. It's like the double death when a black hole dies yet again. Black holes merge in their final fall into one another, and then they produce a really bright, really loud flash of gravitational waves. And that was discovered in 2015 and earned the Nobel Prize a few years ago. There was another thrilling discovery just 2 years later, analogous thing, but instead of two black holes, it was two neutron stars fell into one another. Amazing thing in this case, the black holes did not produce any light as far as we know, only gravitational waves. So that's a great example of the complementarity of these different messengers. So I've shown the value of studying Crab Nebula and other objects across the electromagnetic spectrum. We're now getting into the value of studying beyond the electromagnetic spectrum and also studying in other senses, in other messengers. So not just light, but also now gravitational waves. There's this complementarity where we understood the black holes because of gravitational waves and without light at all, and all the other objects that we've seen with light and not with gravitational waves. And now in this case, we saw it with both light and gravitational waves. And the type of light that we saw it with was gamma rays. So gamma rays, in this case, in many cases, are the key bridge from these new messengers like gravitational waves to the entire electromagnetic spectrum. Once you identify it in gamma rays, then you can also study it in other parts of the electromagnetic spectrum. So here's what happened in 2017 when this merger was detected. It was detected by the Fermi NASA telescope that I mentioned at the beginning, and also by the LIGO gravitational wave detector. And here's a video of what that looked like. So you're going to see, as a function of time, what the gamma ray signal looks like, flash of gamma rays from this merging neutron star system. In the bottom, you're going to see a gravitational wave signal, which you can think of as an analog of listening to an object. And so people have sonified that information. So I'm going to play that with the sound on. Let's see gamma rays at the top, gravitational waves at the bottom. So this was the culmination of many, many.
I would have chosen.
Too cute to be real. Okay, you guys are harsh audience. They did both pass peer review for whatever that's worth. I guess they didn't send it to you for review. Do it again. So I think this is an amazing, a triumph of humanity. I hope I'm not being too sentimental to say that. You know, decades, centuries of work by humanity, I think, resulted in many things, including this. So a lot of amazing instrumentation technology went into this Fermi NASA telescope. The same for this gravitational wave instrument. They were synchronized. They all knew the exact absolute time with GPS to a sub-second precision. And so you can say that these two things happen in the same direction at the same time. And that tells us right away lots of physics, including that gravitational waves travel at the same speed as sound, same speed as light. Going back to that first concept. It also tells us that actually this 1.7 seconds delay from gravitational waves to the gamma rays is meaningful and tells us something about the physics of this merging. Lots of amazing. Yeah. What causes it? It means basically there are these two really dense objects that are forming, that are merging. So they merge before the process that produces the burst of gamma rays. And so it takes some time probably for some jets of matter to form from that merging system and make it out of that initial system. That's what's causing that delay. And I didn't really go into this yet, but this is called a gamma ray burst. It's analogous to the exploding star that I mentioned before, but it's a different type of gamma ray burst. This is formed by the merging of two neutron stars rather than the death of one star. Okay, another brand new messenger that's famous here in Madison especially is neutrinos, led by the IceCube Observatory. So we can now study the universe using not only all the types of light, electromagnetic spectrum, all the types of gravitational waves, but also neutrinos. And there have been a number of discoveries by IceCube, including a couple years ago, one that also relies a lot on gamma rays or is much more powerful in combination with gamma rays. And that is, we detected that there's one of these giant black holes, not the small ones, like the ones that merged, that are comparable to stars, but millions or billions of times the mass of the sun. So one of them at the center of a distant galaxy, that particular galaxy that I chose at the beginning, NGC 1068, about 50 million light years away, one of them is a bright source of gamma rays and of neutrinos. And in fact, it's bright in GeV neutrinos, billions of times more energy than we see with our eyes, and not in TeV neutrinos, billions of times more energy. Despite being bright in neutrinos, which I haven't mentioned the energy of those neutrinos is at the trillion TeV energy scale. And so somehow this object is producing a lot of neutrinos without producing a lot of gamma rays at the same energy. And so by combining that information, we can infer that the gamma ray, so we know from the physics that's producing them that it's actually the same process, it produces the neutrinos and the gamma rays, and therefore they're produced together, but somehow the gamma rays disappear. That means that they're being absorbed. That means that this whole process must happen very close to the black hole. So we're actually studying the physics within a small number of radii of black hole itself, about 30 radii of the black hole. And we're learning about the basic physics that we couldn't imagine any other way. This optical image is zoomed out many orders of magnitude beyond that direct distance right next to the black hole. So to recap that, gamma rays combined with the rest of the electromagnetic spectrum are a key to multi-wavelength astronomy, studying the universe in lots of different wave bands. Now we're also doing it not just with our sense of sight, but also with lots of other senses. So that's the multi-messenger astronomy. And most of the most important multi-messenger discoveries that have been made so far, especially those that combine the electromagnetic spectrum with other messengers, have been made thanks to gamma rays. So they're the bridge from other messengers back to the electromagnetic spectrum. So these are some explosions and some interesting transients that have occurred in the past. It's a difficult science because we don't know when and where to look. We just have to kind of look in all directions at all times and hope that we find something. There's a rare exception to that, which probably a lot of you have followed in the news, which is a somewhat predictable explosion coming up in the sky. And that's a nova called T Coronae Borealis. Here's a plot made by Jesse, one of my students in the audience. This is two historical eruptions that occurred in 1946 and 1866. Imagine what telescopes they had in 1946 and 1866. This is optical. This is a light curve in the optical. So this is the brightness in optical as a function of time in days from 0 to 300 days. And this is a log scale vertically. So there's this really bright flash, and the two colors are the two different times. So there was this exquisite data that was exactly reproduced in 1946 and 1886. That tells us that so there's about 80 years between these. If you add 80 years again, you get to 2026. Some scientists have done some detailed modeling where they think that number varies a little bit, and so it might happen in 2024 instead of 2026. But probably it'll follow this exact beautiful shape again. And so we can predict what the explosion will look like in optical. But in 1946 and definitely 1866, we didn't have gamma ray telescopes, we didn't have neutrino telescopes, we didn't have most of the beautiful instruments we have today. So this is going to be spectacular when it goes off sometime in the next 2 years to observe with gamma rays and lots of other telescopes. So keep an eye out for that. It will also be visible with naked eye, I think up to about magnitude 2. Okay, just a side advertisement, another project that I work on with students, especially, is called the Distributed Electronic Cosmic Ray Observatory. It's a citizen science project, so you might be interested. Basic idea is that we can do a lot of the same science that we do with these gamma rays and other particles using our own smartphones. So when one of those particles collides with your smartphone image sensor, it makes a track, and we can record that beautiful track of that otherwise invisible subatomic particle. And so we have users across all continents and 80 countries. You can also contribute your own data. So this is a highly collaborative field. I haven't really mentioned it, but these projects that I've mentioned are multi-university, multinational. They span hundreds of people and dozens of universities in many countries. And it's really fun to work with all these people around the world, and especially here in Madison. So thanks to the people in my own research group that I work with on a daily basis. Here's especially 2 of the grad students, Zach, who introduced himself at the beginning, and Luca, who helped with a lot of the work here. And then my whole research group here. We had a party a week ago. And the undergrads in particular are impressive. We had a little spreadsheet about how to do the potluck planning, and they said we've got dessert taken care of, and they said they would make multi-dessert Essinger astronomy. And so they made a cosmic ray cake, a electromagnetic wave cake, a gravitational wave cake, and a neutrino fruit assortment. And if a lot of you are probably familiar with Ice Cube, if you zoom in, the fruit assortment is in the same shape and colors as the Ice Cube event display. So it's great fun to work with these students. Extra certified compared to you guys. A lot of fun to work with all these people, so thanks to them. So to conclude, there's almost a cliche in our field that when we build instruments with these new messengers, we're opening new windows on the universe. And so a graphic designer at our institute, Whitback, made that literal with an image, semi-literal, with a graphic design of stained glass panels. And that was just for fun for talks, but then we decided let's actually make it and build it at our institute. It's not actual stained glass, but it's a pretty good imitation of stained glass. So on the left is gravitational waves, in the center is neutrinos, and on the right is the gamma rays I told you about tonight. So gamma rays provide a unique view of the extreme universe up to very high and even what we call ultra high energies, quadrillions of times beyond what we can see with our eyes. We've detected gamma rays over 10 orders of magnitude in energy. We continue to discover them from a variety of different astronomical phenomena that I've told you about tonight, especially those related to the lives and deaths of stars, one of the main building blocks of our universe. And they're the key component, I'd argue, the essential component of multi-messenger astrophysics. They can teach us about lots of astrophysics that I told you about tonight. I also briefly touched on dark matter. They can also tell us about lots of fundamental particle physics, including dark matter. And here at UW-Madison, we're playing a key role in the science, especially through the Cherenkov Telescope Array Observatory. Thanks.
Anybody has any questions, raise your hand and I'll bring the microphone to you.
Is there a theoretical upper limit to energies of gamma rays that people know about?
No. I mean, okay, that's being a little bit flippant. Maybe you've probably heard about grand unified theories. Maybe if you get to grand unified theories, who knows what the particle physics way up there is, but that's still many orders of magnitude beyond where we are now. I'm amazed that, when this paper was published a few years ago at the quadrillion times visible scale, I was amazed by that. And there are new papers every year discovering new objects at even higher and higher energies. So it's really amazing.
What can you tell us about the construct and materials in the sensors on that telescope?
Yeah.
Are they Sony? Is that
Find a better image of it.
so much of the sensors, so I wonder if they're
That can be my bet.
Okay, here's kind of a view of our lab in Chamberlain Hall. So here's the electronics in the back. Here's the sensors in the front. Each of these little modules has 64 pixels, and it's in a dark box here. So this whole camera, after we finish upgrading it, will have 11,000 pixels, which is a lot for this type of science, since each one can time resolve at 1 billion frames per second and with single photon sensitivity. So the sensor here, you can see two, the inner view, front view from here compared to the back view from here. Each of these sensors is called a silicon photomultiplier. And there's one manufacturer in Japan called Hamamatsu. There are a few others around the world. We're partnering with a group in Italy called FBK that makes these. No, no Sony or Panasonic. No. It'd be a lot easier if we could just buy it from them.
Hamamatsu makes the ones for my mass specs.
Okay.
Who does? Hamamatsu, the guys, on mass spec package. Any further questions?
Okay, Preston, I apologize for the audio difficulties.
Fine.
We thought maybe,
right.
yeah, well, our hypothesis was that it could be defective equipment, but we also consider that you could be emitting energy in the radio spectrum. We should get that checked out.
It could be. I had an arm X-ray this morning. Hope I'm not radioactive.
Well, Justin, on behalf of the society, I would like to offer you a choice of either these very fine items of Madison Astronomical Society swag. We either
I wanted to see a logo. That's a hard choice. How about the mug?
want to be mugged. Very
Yeah,
fine.
hats already. Thank you so much.
Thank you. Thank you so much. And it's great listening to your presentation. It's also very fun to be able to think about particle physics once in a while. I'm probably not the only one that forgets about that fun stuff too when we're looking through our telescopes. So thank you so much for visiting with us tonight, and that wraps it up for this month's Astronomical Society meeting. And the next meeting will be on Friday, September 6th, and the following week on Friday at September 13 will instead be at the Monona Terrace having our star party. So we'll see you then, and thank you so much for joining us, and have a good night, everyone.